Look at the extreme bubbling in this footage. When reactive metal meets acid, the physical reaction is immediate and intense. Today, we are going to control a reaction very similar to this one. We will react solid zinc with dilute acid to produce hydrogen gas and thermal energy. Before we handle any corrosive liquids, you must equip your chemical-resistant gloves and secure your safety goggles. This image shows exactly what you need at your workstation: zinc granules, a clean test tube, a dropper, and a bottle of dilute hydrochloric acid. Make sure your test tube is completely dry inside and seat it securely in a standardized test tube rack so it stays upright. Setting up a precise, secure workspace is our first required step. It allows us to safely bring a volatile chemical equation off the chalkboard and into the real world. Using a spatula or tweezers, carefully transfer a few individual zinc granules from your watch glass directly into the bottom of the transparent test tube. Look at the base of the glass. You want just enough zinc pieces to cover the very bottom in a single layer. Next, take your dropper and extract a small amount of the dilute hydrochloric acid. Place the tip of the dropper near the inside lip of the test tube. Slowly squeeze the bulb to drip the acid down the interior glass wall until the zinc is entirely submerged. Never pour acid directly from the primary stock bottle. Doing so risks a dangerous chemical spill and an unpredictable reaction. Adding the acid drop by drop keeps you safe and guarantees a steady, observable reaction, preventing an uncontrolled surge of gas. The moment the liquid acid makes physical contact with the metal, focus your attention right on the surface of the zinc granules. You will see a vigorous fizzing start almost instantly. In chemistry, we call this physical reaction effervescence. In this macro footage, those rapid, continuous bubbles escaping directly from the rough metal are hydrogen gas actively forming and rising. Keep watching as the initial surge settles. Verify that the gas evolution remains continuous and steady, streaming upward through the liquid. This visible effervescence is exactly what we are looking for. It is direct, undeniable proof that the zinc and acid are currently undergoing a chemical transformation. Now, take your gloved hand and gently press your palm against the lower outside wall of the active test tube. Pay attention to what you feel. You should notice a distinct warmth radiating through the glass against your skin. Look at this diagram. When a chemical process releases heat outward into its environment, we formally define it as an exothermic reaction. Feeling that unexpected heat against your glove is physical proof that thermal energy is an active, invisible byproduct of this exact chemical change. We can feel the heat and see the bubbles, but to understand why they happen, we need to look at the underlying molecular mechanics. On screen, you'll see our starting solid component, one atom of zinc, represented by the symbol Zn. To that, we add our liquid component. The equation expands to include 2 molecules of hydrochloric acid, or 2HCl. As the acid touches the metal, the existing molecular bonds in the acid begin to break apart. The central zinc atom then attracts and snaps together with the 2 loose chlorine atoms, forming a new solution, zinc chloride, or ZnCl₂. That leaves 2 hydrogen atoms completely isolated. They bond together as H₂ and drift upward as the very gas bubbles you observed. The warmth on your palm and the bubbles in the glass are simply the macroscopic results of this specific molecular rearrangement. Let the test tube rest and observe its final state. If you look closely at the bottom, the original zinc granules are noticeably reduced in size. This checklist graphic tracks our exact results. We clearly observed hydrogen gas, we watched the solid zinc react and dissolve, and we felt the exothermic heat produced. To finish, strictly follow your laboratory guidelines for cleanup. Dispose of the acidic zinc chloride solution in the designated chemical waste container and thoroughly wash your glassware. Great work! By safely controlling this volatile environment step by step, you have successfully bridged the gap between theoretical chemistry and applied experimental science.